Okay,
Okay.
you're very welcome to join this talk by Luis Vega from the Basque Center for Applied Mathematics. We are very, very happy to have him with us at GEOTOP-A. And the talk is the binormal flow and the evolution of viscous vortex filaments. To you, Luis.
Okay. So thanks a lot for the invitation. It's really nice to be part of this interesting seminar, right? So many people of different countries and around the world. So as you see in the slide, the title of the talk and also the people who are behind this work, which is mainly in this case is Marco Antonio Fontelos, but most of the things I have been doing, and it will be mainly the last part of the talk. Most of the things that, as I say, that I have been doing with related to the so-called binormal flow with very singular initial data is together with Valeria Banica. And so this is also, in a sense, part of this work. And also, and finally, I have to say that I'm also part of the University of the Basque Country. I have to say I am in both institutions to avoid the problems later on. So let's start. See if I know how to do it. Okay, so I cannot pass it. So which is the problem? Okay, so maybe this was not a good idea. Okay, let's do it this way. Okay, so then the summary is more or less as follows. So first I will show you some movies to clarify what is the kind of things I am interested in. Then I will fix the mathematical setting and will give the results, in particular what we call the desingularization of the Biot-Savart integral. And and then, of course, in this process, I what it is called the localized induction approximation of this singular integral, and geometrically is also understood as the binormal flow of curves in 3D. I will have to introduce it, and then if I have time at the very end, I will mention some properties that do appear in this flow that are, I guess these are properties that people working in turbulence really want to see in any model related to turbulence, which are the so-called intermittency of the dynamics and multifractality. Of course, there is a big jump between, say, points 1, 2, and 3, and if you want 0.4, so the jump is that is as follows. The result I will talk about is on the desingularization of the Biot-Savart integral is a result about regular curves, and the examples of intermittency and multifractality are about non-regular curves. So this jump, we don't know how to make it yet, but is a widely open question. I would say it's a very interesting question. I don't know the answer. I will give you some hints of what I expect the answer to be, but whatever the answer is, I'm pretty much convinced that it will be interesting. The reason is that for the guy who is behind these properties of intermittency and multifractalities is a simple object if you want from the Fourier analysis point of view, because it's nothing but the fundamental solution of the Schrödinger equation on the torus. But at the same time, it's simple because I can describe it in this one line as a Fourier series. But anybody that has looked at this guy with some care knows about the complexity that it is behind this Fourier series. In particular, we will be able to describe objects as the one you see here, which, for example, in the previous one, you see on the top, there is m equals 3, which comes from triangle, as you will see. And if I change it in m equals 4, it will be this the picture, which is a square. And the only thing that changes of the trigonometric series is just the cm you see as a constant multiplying the sum. So hopefully we'll have time to go all the way up to showing you these pictures, but just in case it is not possible, I rather do it. I rather doing it at the very beginning.
Out of like a hole,
So
which is the way.
this is the first of the videos. So well, as you see here is very simple. It is just the evolution of this vortex ring. And in here, of course, the question one could ask is, what is this guy you are seeing here? I guess you could imagine it's a center of something, and in particular should be a circle due to symmetry. And also, what are all these? You want all these guys going around, and of course, what is the speed if you want? Of course, the geometry here is very simple, and I would like to complicate it. And in order to do it, I will have to go to a more sophisticated geometry like this one you see. So let me finish the whole video, right? So now I would like to stress a couple of things. So, for example, at the very beginning, it is not clear what you see, but suddenly you start to see the filament, if you want, and eventually you identify a very precise shape, which is very reminiscent of the nozzle that you see on behind the screen. And what it is interesting is that this shape, in a sense, is repeated later on, but where all the symmetry has changed, the axis of the symmetry has changed, right? If you want, you go from this shape to the previous one, or the other way around. And also, imagine that I decide to show you what's going on here. Quite likely, it's not so easy to say that you have a threefold symmetry, right? Unless you wait a little bit to see what happens. So, but still, the questions are the same, which are who is this guy, and can I describe which are these bubbles around, and mainly, probably the main question is what is the speed, right? And what is the law that governs this dynamics? Then I can complicate a little bit and a little bit more the geometry, and this is kind of a fascinating experiment done by the people in the University of Chicago. Let me finish it. It's by William Irvine and collaborators, where quite likely, I mean, again, of course, you could ask the same, right? What is this guy? That depends heavily on the shape that you have here, which is the substitute of the nozzle you saw before. And again, is what is the size of these bubbles are going around? And finally, what is the law that is determining these dynamics? In this example, it seems as if the geometry is frozen, and that the filament, the center of the filament, or the center of the tube, let's put it this way, it exists and is moving without a change of shape or form. It's like it's kind of rotating and moving upwards, if you want. Anyway, so these are the three examples, and what I want is to try to describe this in a precise way. And of course, in order to do that, I need some math. And this is the second part of the talk. So I am dealing with fluids, viscous fluids, and one of the most elemental most of fundamental elements in fluid mechanics are what we call vortex filaments, which is nothing but a concentration of the vorticity on a filament. And these kind of structures have paid, I mean, they have been a central theme since the early days of fluid dynamics, and you have there some well-known names like Helmholtz, Kelvin, Kirchhoff, and others. And mathematically, the kind of guy we want to describe is given, as you see on the slide, is just saying that the vorticity that they call little omega at the time 0 and the position x is nothing but a vector measure which lives in the curve chi, right? And is a delta on this curve. The strength of the delta measure is gamma over 2 pi, just think in terms of gamma. And because omega has to be a vector, the direction of this vector measure is nothing but the tangent vector at a given point of the curves sigma, right? So here, capital X, this little x is nothing but chi of S0, right? So I am parameterizing the curve according to the parameter S that eventually you will see that can be taken as an arc length parameter. So the length of this guy will be 1. So that means that in this description, we are identifying the tangent vector, and this is important what I'm about to say. The tangent vector of the curve chi will be nothing but the direction of the vorticity, right? Which is a quantity that has turned out to be rather relevant. Anyway, so this is the starting guy. And now I have to introduce the velocity, and of course the velocity is in fact is the other way around. If you want, given the velocity, if I define the vorticity as the curl of the velocity, I will assume that the divergence of the velocity field is 0, and then it's a very nice exercise of vector calculus to try to really, not to try, but to compute what is the formula that gives the connection between the vorticity and the velocity, which is the one you see on the slide. Is nothing but what it is called the Biot-Savart integral that, as you see, is singular, right? Because as soon as x is not in the support of the vorticity, if I assume that I am in the previous example and at t equals 0, then this will be nothing but a contour integral along the curve sigma. So if x is outside, then of course the kernel is analytic and there is no problem. But you would like to compute the velocity precisely at where the filament is, and then you have a very serious problem because the kernel, it grows like the inverse to the distance to the filament to the square. So when you integrate once, that will mean that the leading term will be kind of the distance, the inverse of the distance to the filament. That of course diverges. And this is what it is called the desingularization of the Biot-Savart integral problem, right? So because this leading order, which is like the inverse of the distance, is precisely rotating. This is very well seen if you take just the curve sigma to be the straight line. Then the leading order, the velocity around the filament is rotating, and then the leading order doesn't play a role and does not move the filament. So you have to go to the next order, which would be like the kernel will be like the inverse of the distance. So you don't have a symmetry or such that you can define the integral as a principal value. Then a log will appear. And in fact, as soon as you have curvature, then you, as we will see later on, you don't have such a symmetry, and then you have a logarithmic behavior close to the curve, which is what you see at the bottom of the slide, right? It is here. So you have imagine that the distance to the curve is epsilon. Then the computation, which is not so complicated these days, but not so obvious either, will be of this type. So the strength will be gamma this time multiplied. There is a 4 pi in this case, multiplied by the curvature at a given point of the say at the closest point of the point x. So you're assuming that x is outside at the distance epsilon, and then you have to fix to find what is you will see a picture in a minute, what is the point along the curve which is closest to x. And this is the leading order. And the next one is, the next term is an O of 1. Okay, so let's continue. So as I said here, omega gamma is the velocity, kappa will be the curvature, S is arc length parameter, and B stands for the binormal vector at the position S at the time t. So if you neglect this O of 1, then you obtain what it is called the local induction approximation, because these logarithmic terms appear just because of the local behavior of the singularity. And this is a very old story that Renzo Riccarelli is probably the expert in this, and it's kind of a fascinating story. And I do recommend his paper about how this model has appeared and disappeared along the history of fluid mechanics, because the very first time that it is documented is in 1906 by the Rios, that at the time was a student of Levi-Civita, who was very much interested in this problem. In fact, even in 1932 he published some results, and my belief is that, for example, the third video we have seen before is very much related to the examples that Levi-Civita found in so long time ago. I mean, all right. So now I have I have characterized my initial condition, and the question is, can I say that there is a solution of this problem? So I have to determine what is the equation, and I will, because I have really a singularity. So unless I find a way of regularizing the singularity, or I will not be able to say how it is moving. So for us, we will consider Navier-Stokes as a regularization process. So that means that you are using the viscosity, you are introducing viscosity and this friction among the fluid elements. And then this becomes a PDE question where you have and I will not write the equation, just Navier-Stokes, which is Newton's law, where you are adding an extra term, which is given by the viscosity. So it is a PDE that you are fixing the initial condition. So, right, the solution is then, can you say that there is a solution, and is it unique? Do you have continuum dependence? And it took quite some time, but there is a very beautiful result already old of 1989 by Giga and Miyakawa, that they succeeded, and not just for one filament, but for a finite number of them. And so it's a very, very general result, because they construct the solution using not the energy method, but using the perturbative argument based on Duhamel's formula and Picard iteration. The idea that these old ideas of Picard iteration and Duhamel's formula could be useful in fluid mechanics, it took a lot of time to appear, and as far as I know, argue to cut off in the early 80s. And then Giga and Miyakawa, what they did was to use as a functional setting something which are called as Morley spaces. And of course, at some points you have to deal with some singular integrals, and really that the singular integrals behave properly with respect to these Morley spaces was done in the 80s. So I guess if you put all these facts together, then quite likely you could not expect this result to appear until the late 80s, which is really what happened. But in any case, for us, we have a solution, and also we need an extra hypothesis, which is, and it's a very important one, that it is really a perturbative, and it is due to the argument that it's perturbative. So you need some kind of smallness, and in this case is what is called the Reynolds number, which is just that the vorticity over the viscosity, the gamma, is small. Anyway, so then what I really want to do is to convince you that, in fact, Giga Miyakawa solutions describe what we have seen, at least for some relevant times, not too long, but not too short either, the videos we have seen. So I'm not constructing new solutions. I'm describing the solutions constructed by Giga Miyagawa, so that for the particular case of the vortex filament, in order to say what is the dynamics, because one of the problems with the Giga Miyagawa result is that in fact it's so general that the norm it is used, which is the Morrey-Campanato norm, is too weak. And then the information, at the end of the day, the information you get about the solution is very small. Okay, so in order to do this detailed description of the solution, we will construct the solution in a different way. And the starting point will be to use the localized induction approximation by changing the epsilon we had before with just the log, the square root of nu t. It's something that I guess everybody was expecting, right? So really to desingularize the Biot-Savart integral is going is the same in our case as to say that epsilon is precisely what it is called the viscous scale, the square root of the viscosity times the time. And of course, once you have this law, it's a question of just changing time, reparametrizing time to kill the term, the log, and also this constant. So you can reduce just to this simple model, which is curvature times the binormal. In fact, because this is, as I said before, a result that only sees this local singularity, so this term does appear as the Taylor expansion of around the point where the singularity is. So really the flow can be written in this simple way. And here the only thing you need is C2, right? Which is, and of course, I'm insisting in this because with this definition, you could also imagine that the curvature is zero. While if I just say curvature times the binormal, then you have a problem defining the curvature because you would need the curvature being positive. But that issue does not exist as long as you see the flow in this way. Of course, here S is important. You remember that S is arc length parameter. Okay. So let's keep moving. And of course, I have to say a few words about a previous result. Is not just Giga Miyagawa. There are many results, and you see here just 9 of them. And but there are many others. I will not insist too much in all of them. I will just mention probably the results by Gerard Smets, where they made a very nice parallelism between Euler and the binormal flow, and Gerard size, where they give a first result assuming that as soon as you have a vortex tube, meaning that you have fatted the filament with the epsilon I mentioned before, then if you have a nice description of how the vorticity is spread out on the normal plane, then really you could pass to the limit in the viscosity and conclude that the leading order, the evolution is given by the binormal flow. Then more recently, it was, in fact, it's appeared last year, I think, or 2 years ago, but it's an old result. Maybe, no, it was 22. By Bedrosian, Germain, and Harrop-Griffiths, the relevance of this result is that they were beyond Giga Miyagawa, and they avoiding the smallness condition that Giga Miyagawa need. So this is really a step forward because this is a non-linear PDE, and to avoid the smallness is always an issue. But unfortunately, they don't describe the dynamics because we are going to use a similar argument to them, to the one used by these three guys. Harrop-Griffiths is just one researcher, but they treat the curvature as a perturbative, a small perturbation of the leading order. And so that they are not able to capture the curvature. And if you don't see the curvature, you don't see how the filament is moving. So in a sense, this result is very deep, but it is in a different spirit to the one I am going to talk about. And finally, I want to mention the work by Gallet and Sverak that appeared in Archive last year and has been accepted in Invenciones this year, which is again is beyond Giga Miyakawa, but it is at the same time is very restrictive because it only considers where the filament, if you want, is the circle. But of course, they avoid the smallness conditions on the strength, the gamma over the viscosity, and they are able to describe it for all times, right? So this is a really deep result that was very much expected in the community. So maybe, I don't know, it could be a good time to stop. I don't know if anybody for a while has questions. Otherwise, I will continue.
Luis, I have a
Any
very simple
questions?
question. I was wondering if all these works you mentioned on the slide deal with viscosity, one way or another.
Most of them, yes, I would say. Most of them, yes. The result by Gerard and Sayes and Gerard Smets are precisely in the direction of, probably Gerard Smets no, but Gerard and Sayes is precisely in the direction of what happens if the viscosity is small, is going to zero. Okay.
Thank you.
All right. So then I continue, right? Okay. So now let's try to describe the results. I will add, so there will be a picture here. So I will try to go fast in this slide. So so let me go back to this way of doing the presentation. So in order to construct the solution, somebody has to give me a family of curves that solve the binormal flow. And the curves has to be closed. They have to be smooth. In particular, I will need the curves to be C3. And I assume that the time of existence, say, is 1. So that means also, and I assume that they don't have self-intersection. So if that is the case, I will have the curvature under control, and I will be able to define a tubular neighborhood of the curve for and the size of the tubular neighborhood will be fixed, which will be of this order, the inverse of the curvature. So this is the very first scale I have to fix that, as you see, is dictated by the curvature. Once I have that, and you will see it in the picture, I will introduce in the normal plane to a given point of chi some cylindrical coordinates where the vertical direction will be the tangent, and then rho and theta will be the radial and the angle, the radius and the angle, although rho will be really the distance renormalized by the viscosity scale. The viscosity scale is what I call the square root of nu t, because, of course, we are dealing with Navier-Stokes, right? And then I will also, I will introduce different frames to describe the geometry inside of the tube. One is the ER, the usual ER and theta of cylindrical coordinates, where ER is nothing but the position vector of X in the normal plane, and theta will be the rotation, right? Which in this case is very easily written as the cross product of the tangent vector with ER. And also, I will introduce the normal and binormal vectors, saying that when I put everything in cylindrical coordinates, cosine of theta will mean the normal, and sine of theta will mean the binormal. So this is the picture. So I have my curve, right? That is, say, this one, like the one we have seen in the movie. Then, well, you saw in the movie that really the curvature didn't seem to change too much. And in fact, we have the solutions of the binormal flow with this symmetry, so this is not an issue. Then somebody has to give me the curvature is more or less under control. So say the tubular neighborhood will be the green one, r is the distance. And then at any given point, I look at the tangent and then I put cylindrical coordinates here. So because the leading order is going to be dictated by the local singularities, I can always think that close to this point, what I have is something like what you see here. This will be my local tubular neighborhood, and then this distance will be a square root of nu t. Okay, so this is the picture. Now this is the result. So as I said, you have to give me a curve with 3 derivatives, and it will be clear why do I need that. And then what I say is that the Giga-Miyakawa solution that exists up to some given time, which will be of the order of, if I fix this to be sufficiently small, that means 1/10, then this will be of the order of 1/50. You want everything of order 1, but it's dictated by how small is this. And if this is very big, then this becomes smaller, right? But remember that what I do want, although this seems a real abstraction, it is not such in the sense if you pay attention to what I want to do. What I want to do is to see how the singularity I have at time 0 desingularizes due to the viscosity. And of course, viscosity starts to act very fast. So I am going to see the singularity only for a small time. So this is precisely the time I need. And which is the outcome? The outcome is that the vorticity at a given time, position x, it will have different terms, and I do an asymptotic expansion in the small parameter, which, as I said, is the square root of nu t. And the interesting thing is the first 3 terms, they do point in the tangent direction. So this is really the direction of the vorticity doesn't change. Right? The only thing that changes is how the vorticity is distributed along the normal plane, if you will, which is precisely the amplitude of the measure. And here, of course, this is for the experts in the audience. You will recognize here what is called the Lamont-Sim vertex, which is nothing but the Gaussian, the fundamental solution in 2D, because this lives in the normal plane of the delta function with a strength gamma. And this is the right power in 2D, and rho, remember, was the distance renormalized by the scaling, the square root of nu t. So this is precisely what Harold Griffiths and collaborators, Germain and Bedrosian, did, was to take this guy, which is known as explicit solution in the straight case, in the case of the straight filament, and then to treat the rest as a perturbation, right? And then they are able to not to avoid the smallness of this guy and to construct a solution for all times. But then they lose the information about what comes later on. And this is what we add here. So we say that the next term acts in the direction of the normal, because remember this was the cosine of theta. It appears the curvature, and of course you have gained a power of a square root of nu t, right? But still it's in the rho. It turns out that in order to construct this guy, which is really the one I want to capture, right? Because it's the one that has the geometric information, I have to go to the next term, which is still of the same size, 1 of the square root of nu t, but it is quadratic in gamma. Here it is. And involves the 2 directions, but still points in the, so this is the amplitude, so this is an scalar, but the direction of the vorticity still is the tangent of the curve at x at rho equals 0. So as I said, this is gamma squared, and of course here I am using that gamma is small because I have to say that this is small with respect to this. Okay, and finally, what I conclude is that there is an error term, which is in terms of the small parameter is much smaller. Here it is. I'm computing the L2 norm square, so it will go like the L2 norm would go like a square root of nu t, but some log of nu t appears. We don't know if this has to be there or not. Quite likely It has to be there. And so one of the problems of this description, but I will not enter into this too much, is that the error is measured in the energy norm, while the leading orders is given point-wise, so it's an L infinity norm. Of course, in any case, this is much smaller than this kind of guys, meaning that when I compute these three terms in this norm, then the power is of this one was like the inverse of the square root of nu t, and for this one will be like O of 1. So this is much smaller. All right, so this is the result. So in geometric terms, what we are saying is that this is the viscous. So I'm describing it locally. So at a given time, I construct the viscous tube, but I also say that inside of this viscous tube, there is I can look inside this viscous tube and create some other tube, right? Where if you want, let's look at this picture first. What I'm saying is that I'm describing the vorticity inside the viscous tube, and the one you see in black here is nothing but the Lamosin vortex, which is the one of, if you will have a straight filament, which is the Gaussian, the variance is the square root of nu t, and the amplitude is like the inverse of nu t. But due to the curvature, a perturbation appears that tilts a little bit, shifts a little bit the Gaussian and moves it in the direction of the normal. But what it is important is how is this distance? This distance is much, much smaller than the viscous scale. It's of the order t log of nu t times the curvature. The curvature in my case is of order 1, so essentially this is the relevant parameter. All right, so it's like we are able to go inside, and in order to and we are able to say something else. But in order to do that, I have to go very close to the what I call the center of the filament. So unless I am able to move with the right velocity this tube, or I will not be able to see this tiny tube, right? And this is where the binormal flow plays a role. Okay, so let's continue, because I guess I'm getting out of time. So because I really want to convince you that in order to do this, we have to desingularize the Biot-Savart integral. All right, so let's in order to describe, now I want to describe the velocity. This is to say that I desingularize the Biot-Savart integral. So in order to do that, I have to introduce new guys, which go as follows. So first, I say the leading order, I'm rewriting what you see in the previous theorem. So the leading order was just what we call the Lamosin vortex, that it is written here, and now I have the cutoff of the tubular neighborhood where the parameter was this capital R, right? So this is the direction. Rho, as I have insisted, is nothing but the distance renormalized by the viscous scale, and this is the Gaussian. So this was the leading order. This omega naught was the leading order of the vorticity. So the question is now, what is the velocity of what is the velocity in the case where the vorticity is precisely this formula? This is a very nice and simple computation, and the answer is the one you see on the bottom, right? So it's still of because it's, so what I'm claiming is that this is the Biot-Savart integral of the omega naught. B naught is the Biot-Savart integral of omega naught. And the interesting thing is that now at the origin, at rho equals 0, this guy is 0. Okay, I guess this is a very well known that in a straight, you are in, or at least it's well known for the people who do movies. When you have a hurricane and you are in the middle, in the eye of the hurricane, your life seems to be very, very nice and simple. Of course, if you move a little bit, right? So if rho is distance 1, that means that you are at distance square root of nu t of the eye of the hurricane, then your life is much more complicated because you have 1 over rho, which is precisely, and this is in the direction that we saw before, that we will see in a minute, in the direction of E theta. All right, so once I have this, I tell you what is the velocity, and this is the second result. All right, so let's, I'm saying in this result, what I am saying is what is the vorticity associated to the viscosity, what is the velocity associated to the vorticity we saw before. And then again, I have several terms. Now the leading order is moving in E theta. That, remember, is just saying that it is rotating along the filament, and the V naught rho that I was written before. And you have to put the convenient scale. And now, of course, you have integrated once, so the singularity now is better, and it's just the inverse of a square root of nu t. Okay, so this is really nothing but the straight filament. So the real new information comes with the next term, right? Which is precisely the one you see here. So let's forget a bit about this, which is O of 1 and F of rho and H of rho are precise. I don't want to insist on this. So let's go to really the next term. The next term is the one you expect, which is the one found by Darrios many, many years ago. It's the log term. It points in the binormal direction, and it's multiplied by the curvature, and of course times gamma over 4 pi. And then you have some other terms of order 1, the ones that you mentioned here, that go still in the binormal direction. There is another one that is it is 0 at the origin, and we have a very precise description. But I just want to insist in this one, that because this is the one that really matters when you make rho, 0. Remember that at rho equals 0, right? I'm computing now at the center of the tube that it is moving according to the binormal flow. Then the velocity, the leading order was 0, and the only thing that remains are these guys, because the other ones are 0. So this is really the correction in the direction of the binormal of order 1, so you can compute it very explicitly. The leading order is logarithmic, and everything is multiplied by the curvature, and then this new guy appears, and this is a non-local guy, which is giving you have to, of course, here you are subtracting the singularity you have here, and then you can pass to the limit, and you obtain a non-local guy, which depends on the full curve, right? So this is what I call the desingularization of the Biot-Savart integral. All right, so now in a picture, this is what you see. So before, this was my starting tube. Say if you want the tube that Giga Miyakawa see, and Harrod Griffiths, Germain, and Gales, and Bedrosian see. But now with our precise description, we are able to go inside the tube and see more. So this was the vorticity, and now what happens in the velocity? The velocity, what I saw is that a leading order, the Lamosine vortex is 0. This is precisely what you have here, 0. And it goes linearly growing all the way up to the viscous scale. But then at every time, the curvature is acting and creates a velocity in the direction of the binormal that goes like curvature times the log of nu t. Of course, the threshold, where this the one of the Lamosine straight singularity is bigger, is of the order of this new scale that you find in the problem, which goes like the curvature times t log of nu t. I'm sorry, every time I have t, you have to put nu t here, and there's a nu, which is a viscosity, which is missing. So this is really the result we prove. Okay, so let me just to continue a few words about the binormal flow. This is, I already introduced it, and there is something very relevant regarding the binormal flow, which is that the tangent vector is satisfying a very well-known equation, which is called the Schrödinger map equation. In fact, if you differentiate with respect to S here, then this term gives you 0. So the only thing that can happen is that the S falls here, and then this is what you get. If you think a little bit about this, you will immediately see that this is nothing but the Schrödinger equation, but where the target, instead of being the flat complex plane, is the unit sphere. And if you do a Frenet-Frein, immediately you obtain that this is the curvature times the binormal. It's very easy to see that straight lines, circles, and ellipses are solutions, okay? All right, so now the next interesting fact is something which is amazing. If you go to Renzo's paper, you will see that the results by Darrios and Levicivita were disappear in a sense. People didn't pay any attention until in the 60s, Arms and Hammer rediscovered the approximation. And this created a lot of activity, and in particular, this was in the late 60s, and in 1971, Hashimoto proved the following. He made this transformation, which is, again, to write the polar coordinates, the complex wave psi. And here now, I'm sorry, but what was before kappa has become C, and the reason is that this part is more related to Valeria Banica's work, and then we used to write the curvature as C instead of kappa. Well, to finish the story, what Hashimoto realized is that if you compute, you ask what is the equation that the wave function psi satisfies, amazingly you obtain the cubic NLS, where of course due to the gauge invariance of the geometric problem you have, there is some indeterminacy, and in fact you obtain a system, a family of nonlinear Schrödinger equations that are determined by a real function that depends just on t. And typically, what you expect is that the wave function satisfies L2 conditions like these ones here, so that the curvature square is finite. This could be in the full line, and that the corresponding result was due to Tsutsumi for the cubic NLS. And in the periodic case, and then it was due to Bourgain in 93, and for the Schrödinger map for general solutions, for smooth solutions, is an old result by Sulen and Bardos. But really, Levicivita, what he did in the 32 was to obtain solutions of this guy, written them precisely in this way. So he wrote it as a system in curvature and torsion, and then found some particular solutions that in particular, when you use all these models, you can, and this is a very nice paper by Kida and 81, you can see them, you can characterize what are the so-called traveling wave solutions, and in fact, you can determine which are the ones that have no self-intersection. So the results I have mentioned had some, a priori, as I said, I had to say that somebody has to construct the solution of the binormal flow. Here is the result. Kida 81, for example. There are others. In particular, recently with Claudia Garcia, we realized that even the Kida solution was not, with the Kida reduction you will see in the next slide, you can even construct more solutions. So what is the Kida solutions is you assume that your your curve is nothing but a traveling wave along the curve, and a couple with a rotation. So you are using cylindrical coordinates in this case, but where the vertical direction is just the 001. I mean, the third, if you write in coordinates x, y, z, the vertical direction is z, right? And then this is a rotation in the corresponding plane. And you look for this type of solutions, and you end up with a very well known, which is the elliptic cubic equation, and then you can use senoidal and dinoidal waves to the functions to construct them. And the end of the story is that the T is this way, and of course you can. It's not easy, but Kida does it to determine which are the ones that do not have self-intersections. Okay. And just to finish, if you give me 4 minutes, I want to say what I would like to do next. I would like to describe these type of situations which are out of my theorem, because these situations you have some singularity here, and this singularity creates this type of self-similar solutions. And the question is, can we extend? This is a very old result, very old paper in A78, and we would like to be able to describe this type of solutions. Why? Because we think they are very much related, because definitely they are important, as you see in this video. which is the so-called reconnection problem. Right, so you see here in this structure, and you have all these waves here. Of course, this we are very far from proving mathematically what's happening here, but it's pretty clear that this is a way of creating singularities in physical singularities, at least in Navier-Stokes. And of course, I would like to say that this guy you are seeing is related to the following. And now I am hopefully haven't lost my presentation. Here it is. So this is the self-similar solution of the binormal flow. So I would like to know if these solutions that we understand pretty well are precisely the ones we have seen before. But as you see, the curvature here at time 0 is a corner, is the one given by a corner, so it's a delta function. So this is far from the setting I mentioned before. So in this case, what happens is that the solution will be this type of initial condition that is by no means in L2, because the modulus is a constant here, and then it grows when t goes to 0. But this type of oscillations are very well known, and they are called chirps. And Meyer and Jafar, I mean, made a lot of results. I mean, they were very much interested when working with wavelets to describe turbulence, and in particular, there is an old paper by Arneodo and collaborators which says that you want to describe intermittency in turbulence through the vortex filaments, you really need chirps, and this is probably the most simple prototype of a chirp. I don't have the time to insist too much in this, so just to finish, let me show you 2 other videos. So this is the video you're going to see here is just on the bottom is just this the circle that it is moving according to the binormal flow, and this is a polygon with 15 sides that is moving according to the binormal flow. And this is what you see. What you see here is nothing but the trajectory of one corner. And as you see, you have a very complex dynamics. In fact, this is a multifractal. This it has been proved, and we know who is this guy. Well, if not for m equals 15, we know it for m equals infinity, right? If you do the zoom, we know what is this limit, and in fact is very similar to the one you are seeing here for m equals 15. But if you go and you compute the case of the triangle, this is what you obtain. Again, what you see here is nothing but the trajectory of one corner, which in this case is another kind of multifractal that depends on the number of sides, 3 in this case. But amazingly, this is a simulation done by Gerard and Smets in the paper I mentioned before, and De La Hoz and myself realized that if you put ink here and you follow the trajectory, you obtain this amazing guy that immediately we identify which we thought it was related to the so-called Riemann's function. In any case, so it's periodic. It's amazingly, but it is periodic. So, and if you go to the middle of the period, this is what you obtain, okay, which is very reminiscent of the second video I showed you. And of course, if you leave a little bit to move, you immediately see the horseshoe structure I showed before and the self-similar solution. So, of course, this is the open question. Are these guys really behind the vortex filaments in Navier-Stokes? Because if the answer is yes, you are saying that this guy is really playing a role in the description of turbulence, which would be really amazing. And I guess this is all. Thanks a lot.
Thank you very much, Luis. Beautiful talk. Very good. I wonder if there are questions from the audience first.
I have a question, Renzo. Can you hear me?
Oh,
Yes.
hello, Keith.
Hi, Renzo.
Oh, good to see you. Yes,
Yeah,
go
sure.
ahead.
I've enjoyed this talk very much.
Hi, Keith. Yeah,
Hello
nice to.
there, Luis. I'm
I
sorry I
didn't.
arrived just 2 or 3 minutes late after you had started, but I've
Oh.
enjoyed it very much. The one comment or question is this: in your theoretical work, you assumed that gamma over nu was small.
Yes.
So it's really low Reynolds number. low
Yes.
Reynolds number situation. So I agree, of course, you can describe the behavior, the evolution for a very small time, nu t small compared to 1, but you can't push this to the time, for example, where that triangle, for example, becomes periodic or you know.
Yes, of course. No, I do understand the question, but my claim is that it's a small time, but it is enough to see relevant things. So let me try to explain what I mean. Of course, I am very far from being able to describe this, you see, because here the problem is the singularity, right?
Yeah.
But in principle, for example, in the case of the second video I show of the threefold symmetry, what I am not able to go all the way to the period, but to say one third of the period. So time small means that I'm missing, but I can compute a precise and given time for this. This is one thing. And the second thing is that in this case, you see, because this is multifractal, if I am able to describe it just in this time, by zooming, I see all the complexity.
Yeah.
So really, the question is not the time. The question is how much singular can I be in their curvature at time 0? This is the real problem in order to see a complex dynamics. Of course, what you are asking is, I will very far to be able to describe this. That's fine, because at that time, the viscosity is not clear what it has done. What I am claiming is that I have the expectation, even for gamma, a small Reynolds number, to describe singular dynamics like this one. All right? Because taking very, very
good.
singular,
Very
very
interesting.
singular.
Yes. Thank you.
So the parameter which is big in this case is not Reynolds, but the curvature. This is my new parameter.
Right.
Of course, I don't know how to do it, but it is true that given any size of the curvature, there is a time where I can describe it. Huh? This is the result I have so far.
Beautiful.
Yeah.
Other questions, please.
Yes, Renzo. Yeah. Hello, Luis. Hi. Hello. Yeah.
Oh, hi, Shin.
Hi, Renzo.
Very
Yeah.
nice. I'm very happy of
Hi,
seeing
Luis.
these
Yeah.
people.
Very nice to see you. Yeah. Thank you so much for this beautiful talk. I think a very natural question is to ask about the energy. Maybe you can also track the transfer of energy from one part to another part.
Of course. This is the reason why I insisted so much in this. Let me see if I. Okay, let me see if. So this is the reason why I insisted so much in this picture. You see, what I'm saying is that, of course, the leading energy is in this viscous flow, which is of the order of what you expect, right? And the dissipation will be dictated by the energy, right? By the energy law, right? So it's given by the viscosity. But the important thing is that if I look very, very close to the center, I capture this size, right? So of course, and this is the kinetic energy that it is moving. It is moving the filament. In particular, I will have, because my error is on average, the only real information I have on this is all along this tube, right? So here is really a non-local result. And I would need that somebody tells me that the velocity square, which in this case is the curvature square, is preserved along the filament, because otherwise I will not say it is lower bounded, for example. So in this very tiny, which is tiny with respect to the viscous scale, I do capture the kinetic curvature, which is the one in the direction of the binormal. And this is preserved as long as you say you have your time, that it is not killing you the singularity. You see? So
Okay.
really, I am saying how the, at least I am saying how the curvature, how the viscosity, I'm sorry, how the energy is moving for small times, and it is moving in the direction of the binormal. And that means that if I am able to describe how the energies move along the filament just by the binormal flow, I will also be giving this information for these small times inside this viscous tube. So definitely, I'm giving some information about how the energy is moving. Okay.
Okay. So if we just move to your example of a triangle, can you just
Yes.
show me how the energy transfer from one part to another and then back to the original
Yes.
position?
Yes. Yeah. This is of course, but this is of course this is a very singular scenario that
Yeah.
I of course I'm far from knowing, but I'm really optimistic that to be able
Yeah.
to construct at least the self-similar solution, because you see,
Uh-huh.
Giga Miyakawa still applies. It is sorry for insisting, but here the smallness of the Reynolds number is not relevant. The really important thing is that the curvature is very big.
Yeah.
Of course, that would mean that the tubular neighborhood has to be very small. Yes, but still, if this is if I look inside this tube, I can see all this. I expect to see all these complicated dynamics. All right.
Yeah, it seems like some oscillation of
Of course,
energy wavelet or something.
yeah, this is
Yeah,
dispersion. The waves are moving along the filament due to the dispersion of the Schrödinger equation. You see, this is the binormal flow.
Yeah.
And this is, of course, this is well known, is the Talbot effect, which is the one which is creating this complicated dynamics. You see, it is precisely this guy.
Yeah.
This guy is the one who is creating this complicated dynamic. This is the curvature and the torsion. This is the curvature and the torsion, of course, which is a complicated guy.
Yeah.
Right?
Very
But
nice. Very beautiful. Very beautiful result. Yeah. Thank you so
A
much.
related point. I always thought that under LIA, the length of a vortex filament was constant. Is that not the case?
it is the case. So going back to this picture, you see, if I go to the maximum of the vorticity, which is here, the maximum of the vorticity has shifted because of the curvature. This has moved precisely in the normal direction. So really, if you look at the maximum of the vorticity, then you are not precisely in the dynamics of the binormal flow. You have to make a small correction in the normal flow. And then the corresponding, and in fact, it goes inside, you do it carefully. So that means that for the maximum of the vorticity, the length will not be preserved. It will be smaller. However, for this tube, if you really want to compute all the vorticity inside this tube, and you want to say that the density of the vorticity is the one that comes from Euler, really you have to integrate all along the tube, and you do need that the length is preserved. And for the binormal flow, it is preserved. You see, if you really want to compute all the circulation, I have to compute the vorticity all along the tube. And of course, this is smaller, but this is bigger.
So in
Then
effect,
it's absolutely crucial that the length
I
is
think
preserved.
you are going really beyond LIA. You're going to the next order in some parameter there.
Yes.
Yes.
Which is the curvature.
Yeah.
Yeah, and honestly, I don't think that the smallness of time is an issue here. Really not. It is. Of course, I would like to be able to say I go all the way to the period in the second video, and quite likely this can be done. Here really is to be able to describe for small times how the singularity is becoming smooth. and looking inside these tubes. And in order to look inside the viscous tube, which is the usual scale, you really need good coordinates. And then the binormal flow is the one that gives you these good coordinates, because preserves arc length. And really you create an orthonormal frame. You see?
Okay.
So
Thank you.
Yes, Yasuhide.
Yasuhide,
Hello.
from Japan. I enjoyed your talk. This picture, I think this red one, this shift of the maximum represents plus and minus effectively component, and this is dipole structure, as cosine theta shows. This Moffat and I worked in around 2000, and
okay.
this dipole induces velocity at the center, and this is acceptable. And
Yes.
yes, for I and Valeria Oklov worked for 3D extension, in particular for helical. Then to get precisely all the dipole structures, you may include torsion and the normal component of vorticity.
Yeah.
Not only tangential component. If
Yeah.
you include normal component, then as a full contribution of dipole is well described. I don't work on the Navier-Stokes, but Oklov and I worked on the Euler equations. And then dipole structure is well captured by including your way and also torsion effect.
Yeah.
This
So
is what I remember.
yeah, thank you very much, and I do apologize for just
Yeah.
the names I included in my slide. I come from a completely different group of people, you see. So this and definitely should apologize. Of course, I am very much aware of the work you have been doing and the models that you include. The next one that it goes beyond the binormal flow and the Hirota equation. This is really amazing. And so my apologies for not mentioning you, but anyway, I am very much aware of your work. But for me, it's very difficult to understand it because you look at it from you use different techniques, right? So just to say that for me, this velocity you are saying that appears along the center is precisely this guy. That's the reason why I'm insisting.
Yes. So actually, this is a extension by localized local induction hierarchy.
Yes.
Lang and Parin done.
Yeah,
Yes.
I know, but I haven't done the job yet. This is one for the future. I really want to do the next Taylor expansion and see that it's precisely the one you are putting, you see. But so my apologies, but time is finite and I do my best. But of course, I am very much interested in that. But honestly, my impression is that as long as I don't understand this singular, I mean this non-local integral. This is amazing. For example, I don't know if this integral, this limit can be computed if you have a corner, which for me is absolutely crucial these days. You see, this is a very deep question in harmonic analysis that I didn't even start to
this
look at.
non-local part is not very difficult. Yes, I agree. Yes.
But at the same time, I clarify. So what I'm saying is that I need a small time such that the leading order is this one. So for the kind of thing I'm describing so far, as long as this is controlled, I am fine. You see, I am fine. So anyway, I'm really pleased. I am really pleased that you guys are in the audience because of course I have looked at many of your papers and tried to understand what you did. And I think that now I understand it much better, I have to say.
Yeah, thank you. It's very interesting.
Thank
contents.
you.
Yes.
Very well. Do we have other questions from the audience, please? Okay, if not, I like to thank you, Luis, for a wonderful talk. Thank you again.
Thank you very much. Thank you. It was a pleasure.
Thank you.
Thank you.